Hello, this is Vanessa Foord, research climatologist with the BC Ministry of Forest Lands, Natural Resource Operations and Rural Development. Thank you to the organizers of the Health of Youngstans Forum for inviting me to give a presentation on climate change and drought risk. So this is what I'll go over. How does climate change affect drought? Some precipitation trends. This will mainly be in northern British Columbia because that is the area in which I work. Risk to forest from drought, and then go over a stand level drought risk assessment tool. So how does climate change affect drought? One of the ways climate change is affecting drought frequency in British Columbia is through variations on our jet stream that are caused by a product of climate change called Arctic amplification. I'm sure many folks probably have heard of this term. And basically what it means is that the northern latitudes are warming up much faster than other parts of the globe. As shown by that little figure in the corner there, if you can see in the middle of the x-axis, that's 0 latitude, you go to your right towards 90 degrees north, and our y-axis is temperature change. You can see that as we move further north in latitude, the temperature changes are quite large. And this is because positive feedback loops associated with enhanced warming in our climate system because of the loss of sea ice and snow cover in this part of the globe. So this impacts our mid-latitude jet stream. So the role of the mid-latitude jet stream is to dissipate heat from the equator to the poles. So what this figure is showing is the purple line is a historical jet stream. If it was animated, it would be moving quite fast across your page. But what we're dealing with because of Arctic amplification, our jet stream just doesn't have to work as hard because that temperature differential between the equator and the poles isn't as great. And this leads to a wavier and lazier jet stream, like the blue-red line being shown here. So as you can see, that jet stream can move further north, it can dip quite far south, and it just gets stuck in those large swings for a longer period of time because of that Arctic amplification effect. So this, of course, affects our weather in BC. So what I'm showing here is a summer weather pattern, typical summer weather pattern on the left. What we normally see is the jet stream cuts the province in half. Southern BC is under what's called a Pacific high, or hot, dry weather conditions, and northern British Columbia is under warm, wet conditions. But under this changed jet stream, it can move further to the north, and it can get stuck for long periods of time. So when this occurs, southern British Columbia is hotter and drier, and northern British Columbia is hot and dry. This is a major switch from the warm and wet northern British Columbia is used to. So that can be quite stressful for all sorts of systems in northern British Columbia. So we've certainly seen this occurring in most recent years. Think 2017 and 2018 when we had our back-to-back record fire seasons. Something similar is going on in winter. Again, typical winter weather on the left where our jet stream cuts the province in half. Northern British Columbia is on the influence of an Arctic high pressure system, which is typically cold and dry weather. And southern British Columbia is under the influence of Pacific moisture or low pressure systems that typically bring cool and wet weather. So two situations here. If that jet stream gets stuck in a lower, more southerly position, like the top figure, that means that most of British Columbia is under that Arctic high pressure system and is colder and drier than usual. And then under the other situation, if that Arctic high pressure system has moved further off to the north and gets stuck in that position, then most of British Columbia is under warmer conditions, and typically this means less snow because that warm will mean more precipitation is falling as rain than as snow. But in terms of drought, these two future or current situations, more current situations, mean less winter precipitation overall. And conditions can change quite quickly. If you recall in 2018, and we had the exact same situation in 2017, we were dealing with spring flooding and local states of emergency at the end of May. And then a few weeks later, that jet stream shifted into a dominant high pressure ridge of hot, dry conditions. And we started our record fire season and provincial states of emergency. So on the left, areas of blue are where we had higher than average precipitation. And then if you look at the figure on the right, which is from early September, orange is level 3 drought, which is very dry, and red is level 4 drought, extremely dry. So conditions can change quite quickly under these changes and to our jet stream. Now looking at some precipitation trends. So this is mostly from north central British Columbia. These come from trends from weather station data in these areas shown in the graph here. So we got Fort St. John, Mackenzie, Prince George, Vanderhoof, Wisteria, which is in the Lakes District, Smithers, Terrace, and Prince Rupert. So what I'm trying to show here is if you could just focus in on the bold values, those are the ones that are statistically significant. You can see that mean annual precipitation is declining in Mackenzie, Prince George, and Prince Rupert. It is perhaps declining in other areas as well, though I can't say that with confidence. And note all the significant values of decline for the winter. So, and quite unanimous decline in winter precipitation across all stations. So a 50% decline in Mackenzie winter precipitation, 41% in Prince George, 30% in Wisteria, 37% in Smithers, and 29% in Prince Rupert. So these are quite astounding figures, and we need that winter precipitation obviously to recharge our systems in order to be able to compensate for the impacts of potential hot, dry summers. You can see that some areas are also seeing summer declines in precipitation as well, 30% in Mackenzie and 28% in Prince George. And really there are no huge increases in precipitation in any of this data, the exception perhaps being fall in Fort St. John. So just a little bit more detail on some of those numbers. So the top is that 16% decline in mean annual precipitation for the Prince George area, where 9 of the last 10 years have had below average precipitation. 3 have been within the 5 driest years on record, and 2010 was the driest year. The bottom left graph is showing Smithers winter maximum snow depth, and there's a 29% decline in maximum snow depth for that area. And then the last figure there is showing days with rain throughout the growing season. In climate, we define the growing season as May through September, and that graph is showing a 37% decline in growing season days with rain. This is a little bit more information for the Smithers area. Note that 35% decline in winter precipitation and potentially a decline in mean annual precipitation for Smithers as well, although I can't be confident on that. But what I want to show here, and which is quite typical of many stations across northern British Columbia, is there are large increases in temperature trends. In particular for the Smithers area, large increases in maximum temperatures. Look at summer increase of 2.4 in the hottest days of the year. So you can see that precip might be increasing in the summer on the order of 7%, but if temperatures are going up a couple of degrees, that's probably leading to moisture limitations in a number of our systems, just because of the effects of evaporation and evapotranspiration leading to moisture loss. So now I'll talk a little bit about the risk of drought to our forests. So I've alluded to moisture stress. This is a graph from Prince George growing season for total precipitation in the blue bars and mean temperature in the red. So what it's showing here is a 17% decline in growing season precipitation. At the same time, a 1.5 degree increase in mean temperature, likely leading to a loss of moisture, enhanced evaporation, low water levels, soil moisture deficits, vegetation stress, and increased drought risk as these trends continue. I get asked quite often, is drought related to fire risk? Of course, this is a complicated answer because of fire suppression activities and the way we manage our forests. But when I hear the Wildfire Service folks say that over 90% of fire suppression is weather, and I think back to those slides on the stagnated jet stream that we've seen in the last few years, it's really challenging to put a fire out if it doesn't rain for 6 weeks. And I think that's where the most concerning links between drought and fire risk come in. The graph is showing the red bars average area burned for the Dominica region from a period of about 1919 to 2018. And then the blue line is growing season precipitation. And what I want you to take from this is that recent large areas burned in 2015 and 2017 occurred during the lowest growing season precipitation. Moisture limitations also limits ecosystem productivity. This figure comes from some of my collaborative research on the impact of the mountain pine beetle on our forest carbon budgets or net ecosystem productivity. So basically, we want our forests in British Columbia to act as sinks for atmospheric carbon dioxide. We don't want them to be sources of that greenhouse gas. So this study is focused on how is the ecosystem recovering post a major disturbance like the mountain pine beetle. And as an aside note, one of the things we found was in 2014 and 2015, which had very low growing season precipitation coupled with very warm temperatures, the ecosystem productivity was much less than we expected during these years, which we had hoped to been in more of a recovery mode. So we know that, we assume that moisture limitations probably limits ecosystem productivity in many places of British Columbia, but also this perhaps has implications for our forest carbon balance. Dry springs are also a bit concerning. So if we look at 20-year trends, in the Prince George, Fort St. James, and Mackenzie area, we can see that if we just look at the last 20 years, spring precipitation has declined quite a bit, while spring temperatures have gone up. Summer precipitation has declined in the order of 66% in the last 20 years in the Prince George area, while summer temperatures have also gone up. And the growing season dry spell length has increased by 29 days in the Prince George area and 19 days in the Fort St. James area. What we're seeing in the springs more typically is earlier snow melts due to this lack of precip and higher temperatures. Anecdotally, increasing winds. I don't have any data to back that up, but I certainly have observed that myself and heard that from many other people who are out and about in the spring. And this can, of course, lead to desiccation of vegetation on the ground when the snow melt has gone, and it helps sublimate our snow melt as opposed to it reaching into the soils. So therefore, we have soil moisture limitations from these scenarios. We're not storing moisture in the soil for those hotter, drier conditions later in the summer. Also, if we don't have enough recharge in the spring, as all our vegetation goes through its spring flush, then we might be limiting the amount of precipitation that makes it to our streams and rivers and contribute to low flows during this time of year. Spring fires may be increasing as well. If you think back to 2016, that was when the devastating Fort McMurray fire occurred. At the same time, this was mid-April 2016, there was also a significant fire in the Beaton River area, and this had to do with low snowpack, early snowmelt, and very warm conditions for that time of year. It was above 32 degrees. And so also if we have this spring drying trend, forest pests like to take advantage of that. There's lots of aspen leaf miner in this part of the province, in many parts of the province, I should say. And they might be taking advantage of the spring dry conditions when the trees are stressed just after flushing. And then also our entomologists have noted that the current spruce beetle outbreak in the Dominica is likely related to these extreme declines in summer precipitation. So we've done a little bit of work related to validating our stand level drought tool, which I will get to in just a minute, on looking at tree growth from tree cores in hybrid spruce in the Dominica region. But what I want you to take away from this information is when we average tree widths, tree ring widths from the period of 1995 to 2005, those average widths are larger than 2006 to 2016, which was a decade where we had much lower precipitation. So we did see a change between these two decadal time periods in terms of growth in mature spruce tree. So now I'll move on to talking a little bit about our stand level drought risk assessment tool. So this was developed several years ago, led by our former ecologist, Craig DeLong, but we still are running a research project to validate and improve the tool. Craig is still very much involved in that. So basically what the tool does is it takes information about water balance on a stand and it projects the risk of tree mortality in the future. To do this, it needs to have information about daily precipitation, minimum and maximum temperatures, which we can get from weather station or climate model data, and then information about soils in order to know something about the relative soil moisture regime. So we need to know percent coarse fragments, soil texture, rooting depth, and slope position. We can get some of this from editopic grids associated with biogeoclimatic ecosystem classification guidebooks, or from site series mapping, for example, like predictive ecosystem mapping. So basically, the tool takes all this information and then it uses another model called TACA, the Tree and Climate Assessment Tool, to relate different climate conditions to the biophysical needs of different trees. And then we produce an absolute soil moisture regime value per tree species, and then a threshold for that tree species based on where it currently occurs, given all our wonderful Beck field data, and where we think what soil moisture regimes we think those trees wouldn't occur based on our knowledge from all our provincial ecologists. And from that, then we create a risk threshold. So this is an example of what it looks like. We use this actual soil moisture regime values to create our drought risk categories. So each species has a different drought risk, and it's based on where they currently exist on the land base. And then we add climate models to it and figure out how potential changes to our climate might push those tree species outside their tolerable limits for moisture, and then they might be at risk at mortality from drought. So this is what it looks like in terms of its Excel output. So you can download this Excel file from the website at the bottom of the slide. So basically what you would do, and it's available currently for Beck variants in the Prince George, Williams Lake, and Cranbrook TSA, is that you pick your Beck variant, in this case SBSDK, and then you would choose a relative soil moisture regime. I've picked here 01, which is quite dry, and then you get this little graph here. So what the graph is showing is different tree species soil moisture regime values, and that is our surrogate for our drought threshold. So basically, if you are below the line, you're good in terms of your drought risk, but if you're above, there's probably a drought risk. So if we look at the first 3 tree species, they shouldn't really be occurring on a site like this anyways. But if we look at something like spruce, which is showing a low drought risk at its current soil moisture regime, so that's that first blue line. As we move into a climate modeled future soil moisture regime for the period 2020, it potentially becomes just on the border of a moderate risk of drought. And then if we move all the way into the climate modeling period 2080, which is the pink line, it is now at a high risk of drought mortality in that time period. So we can map this out too, as long as we have good site series or predictive ecosystem mapping and good information about our vegetation inventory. So here's an example of a map of projected drought risk for spruce. So you can see on the left, that is the drought risk given a past climate from 1961 to 1990. Lots of greens and dark greens, meaning moderate to low risk of drought for spruce in this area. And this area is in the Fort St. James district. And then if we pop into the future, 2080s, which runs from the period 2070 to the end of the century, we can see a lot more orange and red, which is high to very high risk of mortality from drought to spruce in the future. And then here's another example. This is lodgepole pine in the Puncie Lake area, so that's kind of close to Williams Lake in the Caribou. On the left, using the past climate, lodgepole pine in this area, which can get quite warm and dry, is already at a high to very high risk of mortality from drought. Certainly this area has been hammered a lot by fires in recent years. And if you look at the climate period 2005 to 2035, it becomes even more extreme, with most of the mapped area showing a very high risk of drought to lodgepole pine. And then these maps are showing a more southern portion of the Amanika region. The top left is historical climate drought risk for subalpine fir, so moderate to low drought risk in many parts of the Amanika region. But if we project that out to the period 2040 to 2070 in the bottom right, you can see a lot more orange and even a little bit of red. So that's that high to very high drought risk in that climate modeling period that's really not that far away for subalpine fir. And then the top right is showing the projections for birch in the southern parts of the Amanika region for the period 2071 to the end of the century. There's not a lot of birch, and that's why there's not a lot of color on that map, but you can see a lot of red. So potentially a lot of projected risk of mortality from drought in the future to birch trees. So applications for this type of work is it can be used to inform timber supply. It can use to potentially direct harvesting. So what I mean by that is one might potentially consider going after areas that are at elevated drought risk as opposed to stands that are not. It can also be used to influence hazard mapping, perhaps indicating areas of pest risk, forest pest risk. So if we know a particular area might be highly impacted by drought and the trees stressed in the future, that might be an area where pests would want to take advantage of, and then we could monitor those areas, or perhaps be ready with treatment options if we start to see that occurring. On the flip side, it can also potentially direct retention areas. So where we see green persisting into the future, those might be areas that we want to maintain for mid or longer term timber supply, or maintain just to promote other values like watershed health. And then also it might give us some indications of habitat conditions suitable for different wildlife species in the future. So that's basically it. We were asked to put some key findings together. In the research world, we've been asked instead to start thinking about creating infographics for our research projects. So this was coincidentally created by Jody Axelson and Colin Money and folks in the water research team during a research meeting a couple weeks ago, and I think it just is a lot more fun than a few summary bullets. So thank you to them for that, and hopefully this helps share the message of the concerns about drought, especially given climate change and what that might mean for forest health in British Columbia. Please feel free to contact me if you have any questions or comments. I look forward to discussing this with you further, or sharing any information you might find useful. Thank you very much for listening.